Today I will talk about injectivity and surjectivity. They are defined just the same way as for rings. So we say that a homomorphism of modules, I call it phi, from M to N, is surjective or injective, respectively. If phi is as a map of sets. If phi is surjective or injective, respectively, as a map of sets. And phi is an isomorphism if it is a bijection. And there is a lemma, just as the one that you proved for rings, that a homomorphism of modules phi from M to N is an isomorphism if and only if there exists an inverse to phi. If there exists psi from M to M such that phi psi is the identity of N, and psi phi is the identity on M. Already in the theory of rings, we introduced the concept of kernel, which measures the failure of injectivity. So let phi be again a homomorphism of modules from M to N. Then its kernel, denoted by ker phi, consists of these elements in M that are killed by phi. So phi of M is equal to 0. And I define for phi from M to N, I define its image im of phi as the set of all elements of the form phi of M for M in M. So it is a subset of the codomain. You can note that phi phi is surjective if and only if the image of phi coincides with the target module. And we would like to try and understand what kind of module measures the failure of surjectivity. And we would wonder what would be n minus the image of phi, but it would not be a module in general. So instead, I'm going to consider n quotient by the image of phi. And the definition: if I have U inside M, if it is a submodule, then I define the quotient module as the quotient group, which inherits the structure of the module. And I denote it by M, this line U. It consists of equivalence classes of elements of M. And the equivalence relation is that M is equivalent to M prime if and only if M minus M prime is an element of U. So lemma mod U has a natural structure of an R module. If M was originally a module over R. So let me prove it. First, note that mod U is an abelian group. And it is a consequence of of the construction of the quotient group from group theory. So I'm going to skip this step. And now I define the R module structure on M mod U. So let's say I have an element R in R and the class of M in the quotient. Then I define the result of multiplying M by R as the class of the product M by R, where Rm is the result of scalar multiplication in M. And I want to check that this is well defined. For this I take two elements M and M prime in M, such that their classes are equal. And now I want to check that the result of multiplying by R of M would lie in the same equivalence class as the result of multiplying M prime by R. So let me unravel the definitions. R times M is defined by this line to be the equivalence class Rm. And we know that M and M prime are in the same equivalence class, which means that M minus M prime lies in the submodule U. So I can write like this: M prime plus M minus M prime or Rm prime plus R times M minus M prime. So once again, M minus M prime lies in the submodule U. And because U is a submodule of M, it means that if we multiply an element of U by R, we again get an element of U. So this is again inside U. And therefore, this element lies in the same equivalence class as the element Rm prime. And this is how we define the result of multiplying of the class M prime by R. So, to sum up, scalar multiplication does not depend on the choice of a representative of the equivalence class. And therefore, the R module structure is well defined, and all the axioms follow naturally from the corresponding axioms for R, for M, as an R module. And now that I have this construction ready, I will define the cokernel. The cokernel of a homomorphism of modules phi from M to N is denoted by coker phi, and it is defined as the quotient of N by the image of phi. And recall that I noted that phi is surjective if and only if the image of phi coincides with N. And now that we have this definition of cokernel, if the image of phi coincides with N, cokernel is 0, and so we can rewrite this remark as vanishing of the cokernel. Let me actually write this remark. A homomorphism phi is surjective if and only if the cokernel of phi is 0. And it is similar to saying that phi is injective if and only if the kernel of phi is 0. And in this sense, cokernel measures the failure of surjectivity of phi, and kernel measures the failure of injectivity. So here is an observation about quotient modules. So let's consider U inside M, a submodule of an R module M, and let Q from M to U be the natural quotient map. So it is such a map that sends an element M to the equivalence class that it represents. Then, first, Q is a surjective homomorphism of modules, module homomorphism. And second, the kernel of Q is equal to U. So the proof surjectivity is tautological because for every equivalence class in M mod U, there will be a preimage which we can pick by picking a certain representative of this class. Then Q is a homomorphism. This is also tautological from the definition of the module structure on M mod U, because so if for the addition it follows from the similar result for quotients of abelian groups. And for scalar multiplication, let's consider R times Q of M, and it is R times the class of M, and we defined multiplication as multiplying any representative by R. So this is exactly Q of Rm. And we showed that this is a well-defined structure of a module. And now let's consider what is the kernel of Q. So an element M is in the kernel of Q if and only if its image, which is the equivalence class of M, is 0. And we have that two elements represent the same equivalence class if and only if its difference lies in U. So this happens if and only if M minus 0 or just M belongs to U. And because this is a sequence of equivalences, we automatically get that kernel Q is contained in U and U is contained in the kernel of Q, so they are equal. Applying this lemma to the definition of cokernel, I can derive the following observation, corollary. The kernel of the quotient map from N to the cokernel of phi for some module homomorphism phi from M to N is equal to the image of phi. So very vaguely, you can say that image is the kernel of cokernel. Of the cokernel. And what if I switch the order of these words? I get the definition of the co-image. The co-image of a homomorphism phi from M to N is the following quotient of M. Co-im phi is defined to be M mod the kernel of phi. So you can see that the co-image of phi is equal to the cokernel of the map that embeds kernel of phi into M. Because the image of this map is exactly the submodule that is the kernel. And now I have a language to formulate the first isomorphism theorem in a way that will probably have most of you confused. So let phi from M to N be a homomorphism of R modules. Then the first isomorphism theorem says that the image of phi is isomorphic to the co-image of phi. And to make it less confusing, I will write co-image of phi from the definition. I have M mod the kernel of phi. And if you just compare the left-hand side and the rightmost side, and what the kernel of phi, you will recognize the first isomorphism theorem that we have already encountered for rings and that you have encountered for groups. And the reason I wanted to introduce some additional words is because in some branches of mathematics, cokernel is more easily defined than image. And so image then is defined in terms of the kernel of the cokernel map. And for those areas, formulating the first isomorphism theorem is exactly saying that the kernel of the cokernel is isomorphic to the cokernel of the kernel. But let me prove just the pink part, the highlighted part here. I'm going to go over the proof a bit faster than I did for the rings. So in order to prove this, I define a module homomorphism what we call it psi from m mod ker phi to the image of phi, which takes an equivalence class of m and sends it to phi of m. Just as before, we are checking that it is well defined. But if I take another representative of an equivalence class, let's say m prime, I get phi of m prime, and the difference, m minus m prime, because m and m prime represent the same class, would be inside this submodule ker phi. So it means that phi of m prime is equal to phi of m, which is phi of psi of the class represented by m for m minus m prime in the kernel of phi. So you would want to check that it is a homomorphism of modules. I'm going to omit it because it is a straightforward check. And then we need to see that it is surjective and injective. So surjectivity is immediate from the definition of image, because the image of phi consists of phi of m, where m goes over all elements of m. And so every phi of m is of the form psi of the equivalence class of m, and therefore this quotient surjects onto the image of phi. And it is injective because, as I said, kernel measures the failure of injectivity. So let's say that psi of the equivalence class of M goes to 0. So we are trying to measure the kernel of psi. But this means that because psi of M is phi of M, it means that phi of M is 0. So this is the same as saying that M is in the kernel of phi. But it means, because we're modding out the kernel of phi, it means that the class of M is the 0 equivalence class. And so, indeed, the idea behind the proof is that, or idea behind this theorem is that since the kernel of phi encodes the failure of injectivity of phi, if we are killing it by modding this out, by taking the quotient module, we no longer have failure of injectivity. So this map becomes injective. I will now talk about the universal properties of the constructions that we discussed just now. For a first example, I want to recall something from the part when we talked about rings. So let's say that we have an ideal I in a ring R. Then we can consider the quotient ring R mod I. And I would like to first formulate the universal property for this ring R mod I. So theorem. If phi from R to S is a ring homomorphism such that I, this ideal, is contained in the kernel of phi, then there exists a unique factoring phi bar through the quotient ring, so R mod I to S. Let me draw a picture for this. So we have an ideal I of R. We have the quotient ring R mod I, and I denote the quotient map by Q. And let's say that we have a map from a ring homomorphism from R to S, such that I is contained in the kernel of S. It means that this composition, so phi applied to I, is equal to 0. Then I claim that there exists a unique phi bar such that going this way, so taking phi bar composed with Q, is the same as following just phi. And moreover, this ring R mod I is the only ring up to an isomorphism that satisfies this property number 1, and that kills I. So let's say that R prime is another ring with a morphism Q prime from R to R prime. And this R prime satisfies this property number 1. So if I write R prime here instead of R mod I, and I have Q prime here, then for any morphism phi from R to S, I would get again a unique factoring. And R prime satisfies the universal property 1 here. In this case, R prime is isomorphic to the quotient ring R mod I. Let me prove number 1 first. So we have phi from R to S such that phi of any element of I is equal to 0. Then I define phi bar on an equivalence class R as phi of R. So note that Q, so the map R to R mod I, is a surjection. So this is the only choice that we can make in order to make the composition phi bar Q equal to phi. So we get uniqueness here. So we get uniqueness for phi bar. And now we want to check that this phi bar is well defined. For this, let's say that R is equal to R prime, so in the quotient ring, so R and R prime lie in the same class. It is the same as saying that their difference is in the ideal I. Then I evaluate phi bar at R, and it is, by this definition, equal to phi of R. And I can write it as phi of R prime plus R minus R prime. And because phi is a ring homomorphism, I get phi of R prime plus phi of R minus R prime. But R minus R prime belongs to the ideal, and we assumed that phi is such that that phi kills the ideal I. So because phi of I is 0, we get that the image of R minus R prime is 0. And phi of R prime is exactly the definition of phi of the equivalence class of R prime. And so the image phi bar of R does not depend on the choice of a representative, and so phi is well defined. Phi bar is well defined. And next, we would like to check that phi bar is a ring homomorphism. But this follows from phi, from the fact that phi is a ring homomorphism, and so all the axioms, additivity and multiplicativity, are checked by picking a representative and seeing that it works for phi. And I'm going to move to the second part. And let R prime be such a ring which has a morphism from R. And I will write it here. R prime. And it has morphism Q prime, such that Q prime evaluated at I is 0, so I is also contained in the kernel of Q prime. And let's assume that R prime also satisfies this universal property. And so, to sum up, we have that R prime and R mod I both satisfy universal property formulated in part 1, and moreover I, the ideal I, is contained in both of the corresponding kernels. I is contained in the kernel of Q and in the kernel of Q prime. So okay, since R mod I satisfies this universal property that we have just proved, there is an arrow, I call it phi, from R mod I to R prime. Such that phi q is equal to q prime. But we assume that R prime satisfies the same property, and I is contained in the kernel of Q. So we get an arrow in the other direction, and I call it psi, from R prime to R mod I, such that psi q prime is equal to Q. Now let me consider the composition phi psi. So it is a morphism from R prime to R prime. So imagine if we drew the same diagram as here, but we put R prime instead of R mod I here. Then by the universal property, a morphism from R prime to R prime would be unique. And also we know that the identity morphism, identity of R prime, is such that identity of R prime composed with Q prime is equal to Q. So if we show that this homomorphism composed with Q prime is equal to Q prime, then by uniqueness we would conclude that phi psi is equal to the identity. So now I want to write what this composition is equal to. So phi psi q prime, this is equal to, so note that psi q prime is equal to q, so we get phi q. And moreover, here we assume that phi q is equal to q prime, so we conclude this equality here. And therefore, phi psi satisfies this condition of the universal morphism to R prime. And therefore, from uniqueness, it follows that phi psi is equal to the identity of R prime. And in a similar fashion, you can show that psi phi from R mod I to R mod I is in fact equal to the identity morphism, identity of the quotient ring. And therefore we got two mutually inverse morphisms, phi and psi, such that phi psi is the identity and psi phi is also the identity. And you proved it in one of the p-sets, that it means that both of them are bijections and mutually inverse to each other. So conclude that phi and psi define an isomorphism between R prime and R mod I. And this is what we wanted to show.